Okay, is the mic picking me up? Yes, excellent. Well, thanks everyone for coming to this talk this afternoon about layout polymorphism. So the goal here is to describe an approach that we're working out. This is still all very much work in progress. An approach that we're working out to be able to efficiently compile, to be able to compile code with varying representations into efficient at runtime code. What do I mean by that? So to start wrapping our heads around the problem, we have to think about what is an unboxed type. So that's what I'm going to define in this slide. So if I have a nice type declaration like we see here, and let's say I have p, which is one of these points. Well, the way that this would normally get represented looks like this. So here I'm representing this column on the left could be our call stack. And so we have a bunch of local variables in this stack, and we'll have a local variable p, which will point to a heap-allocated object, which will have a little header, that's those three dots at the top, as well as slots for x and for y. An unboxed version of this would look like this. We have our call stack, and even though I have this variable p in my source code, there's actually just room for the x and the y in the call stack memory. Now, in reality, these would probably just be in registers in the middle of a function, but that's a little harder to represent in a picture here. So this is really what we're talking about. This boxed thing, that's what OCaml has done since the beginning of time. This unboxed thing, that's what Jane Street is doing new and exciting. And so we don't yet have this working. But we are working toward this. So this is our design. Again, this is all sort of work in progress and looking forward to the future. Okay, so with that understanding of boxed versus unboxed, I'm going to make a claim that unboxed types are faster than boxed ones. Right? We have to do less indirection. Right? I don't have to walk to another part of memory to retrieve the fields from my record. I don't have to allocate that memory. I can have better cache locality with unboxed types. But unboxed types are harder to work with than boxed ones. And that's because there's a reason that OCaml uses box types, which is that box types work much better with polymorphism. Right? If in a box type, I know every single value in my OCaml program is going to be represented by one machine word. And that's really nice, and that makes working with the language much easier. So when I have unboxed types, the real reason that they're harder to work with is that they're non-uniform, right? That x and y that we saw on the previous slide, if I want to pass that to a function, I can't do that the same way that I pass a normal boxed value. I have to pass now 2 registers or 2 slots on the stack. So that means that these unboxed types are non-uniform, which requires different runtime behavior. So I now want to introduce this map example here. This is going to be my running example throughout the rest of the talk. So I might have an array of some type alpha, and I want to map a function over that to create a new array of some type beta. That map function must manipulate values of types alpha and beta. And we can see the little color language that I'm creating here. So green here is for runtime values. Blue is for types. And purple is for layouts. So here, what I'm saying is that to be able to, for this map function to be able to manipulate values of type alpha and beta as it's running, right? We have to manipulate the alpha because we have to pull it out of the array and send it to that function. We have to manipulate the beta because we have to get it back from that function and insert it into an array. So it needs to know, is it represented by 1 register or 2 registers? Is it a floating point number? Is it an int? These aspects of alpha and beta are going to control or have to be apparent in the implementation of map. And that's what I mean by map must know their layouts. I can only compile map after I know the layouts of alpha and beta. So this word layout, that's a new term that Jane Street is introducing into OCaml to describe a memory representation, register convention, sort of these runtime details that are necessary to store values of a given type. If you know kinds in other languages, kind is very similar to layout. In fact, layout is a subset of the space of kinds. Okay, so returning to this, here's map. This is the map that we've had since the beginning of time, and so it works over values. But I don't want just value. I don't want just arrays of values. I might have an array of unboxed floats. So here, an unboxed float is going to be one represented by directly by a float instead of by any indirection. And I might want to map over such arrays. So then I have my normal map and I have this map. Well, and then I realize I actually might have an array of values that I want to map into an array of unboxed floats. So I need to have this one. And then, well, maybe I want to go the other way, and I have my array of unboxed floats, and I want to go into values. And now, actually, it turns out that we're recognizing a need not just for 64-bit floats, but we want also 32-bit floats. This is a real need within Jane Street that has come up. So now we want to be able to do that. But then, of course, we want to go the other way. And we want to go among 32-bit floats, and maybe we want unboxed 64-bit integers instead of 63-bit integers. And this goes on and on and on and on, right? So in a real implementation of this, we would need all of these maps. I guarantee you, everything that's on the screen here, we would have to implement at Jane Street among many, many, many more. So really, we know what the solution here is. We want polymorphism, right? This is why we have polymorphism, or I should say parametric polymorphism, in a language like OCaml. It's to stop ourselves from needing to be repetitive. It turns out that actually polymorphism is one step too far for what we need over layouts. And so instead, we need layout flexibility. And I'm going to tease apart what that difference is as we go further. But it comes back to polymorphism in the end. Okay, so let's look at this map here. So what I'm going to do is I'm now going to say that instead of alpha and beta having layout value, we're going to say that alpha and beta have layout any. So this is what I mean by layout flexibility, is that alpha and beta can have any layout. And it's slightly different than what I might use polymorphism for, which would be introducing layout variables. Getting into a description of that would take us a little bit away from the main part of the talk. If you want to, you can ask questions about that. I'm happy to answer toward the end why we don't need layout variables. But here I want alpha and beta to have any layout. Well, what is this any layout? It is a sort of super layout of all possible layouts. And so when I say that alpha can have any layout or beta can have any layout, it means that in that type of map, that alpha can be a value type, that these are all of the normal types that we've known in OCaml, but it can also be an unboxed float 64 or unboxed float 32. It can be an unboxed int 64. It can be one of these unboxed points that we saw toward the beginning, which is going to be a sort of a product layout. And so by annotating alpha and beta with any of those types of any of these layouts or any other that we can imagine can be substituted in to alpha and beta. So layout polymorphism, allowing actual layout variables instead of this colon anything, that would be fine. But layout flexibility is simpler, so we're going to stick with layout flexibility. This is in contrast to Haskell, for example, which does have full polymorphism here. And allows you to have what are equivalent to layout variables. Okay, so then the next question is, so here I have my nice type of map that's going to subsume all of those map types that we saw a few slides ago. So that's great. But how are we going to compile this to efficient code? I said earlier that we can't do that, and indeed we can't. So we could compile this to inefficient code, right? I could preserve the layouts as little tokens at runtime, and then call the map function and look at the tokens and say, oh, once I know the layouts, then I know what registers to access the next arguments in, or I know how to represent this stuff in memory. That's going to be really slow because it requires extra branches at the beginning of every single map. We don't want to do that. So efficient is carrying something here, right? We could do the inefficient thing really easily. But we can't do it efficiently. So what are we going to do? Well, we're going to do layout monomorphization. Right? This isn't a huge surprise. It's what other languages do. And I should say right now that there's no huge twists and turns that I'm going to take in this talk. But building all these pieces together, requires some delicate care. So layout monomorphization. What I mean by that is that this map that works over any layout, I'm just going to stamp out copies of that at every layout that I actually need. And that's the basic idea. But of course, nothing is quite so simple. So there's some details to walk through. So one question is that given that map, exactly how am I going to monomorphize it? So here again is the type of my layout flexible map. The first step to be able to understand how the layouts flow through the implementation is I'm actually going to translate this layout flexible map into the full layout polymorphic one. So this is using some hypothetical syntax that we don't expect to introduce into Surface OCaml. Unlike this, actually already we can type that in and parse it and make sense of it in our branch of the compiler. But down here, this is this sort of hypothetical syntax that I don't think we'll ever implement, where we have layout variables y1 and y2, and once we have those, then in the implementation map, we can easily sort of trace how the layout of this variable flows into some other function, right? Maybe map itself calls another layout flexible function that we'll need to monomorphize, and we need to know which monomorphic instantiation we would need of that function. And so the first step is to use sort of proper layout polymorphism. Then, once we've done that, now we can just monomorphize the thing. And so if we have a usage site that instantiates this map to work over an unboxed float and say a string, which is one example of a value, then we would monomorphize the layout flexible float, which has been translated to a layout flexible map, which has been translated to a layout polymorphic map into this monomorphic one. Although, to be clear, this is still not monomorphic, right? There's still type variables alpha and beta here, right? We're not doing full monomorphization. We're just doing layout monomorphization. And then, once we've done that, we can compile that. So we don't need to know the types to be able to do this. We just need to know the layouts. That's the information that we need to be able to manipulate these things at runtime. In a sense, that's almost the definition of what layout is. It's the stuff that you need to compile something. And actually, as I've discovered in other work, that depending on your compilation strategy, exactly the definition of layout might change. Okay, so then the next question that we have to ask is, so if we're going to do this monomorphization, that means we need to go and find the code to monomorphize. So here, I have somewhere else in my program, I have a call to map that looks like this. So I'm calling map, and here is some function f of this particular type working over some array. Well, to be able to monomorphize map, I need to go out and find the code for map. But the problem is that finding that code is going to depend on my module m. And module m is a runtime value. I don't know necessarily where it's come from here. Maybe it's a first-class module. Maybe I'm in the middle of a functor, and m is bound as a functor parameter, right? In these cases, among a number of others, we can't really know exactly where the code for m.map is. And so then we can't monomorphize it. We need to know where this code is at compile time to be able to do that monomorphization.
But sometimes you do.
Sometimes we do. And we will when we have a static mode. So this is, I'm using the word mode as in sort of modal type theory. It fits into that same structure that you may have seen in our blog post series about oxidizing OCaml to track data race freedom. But another mode in that space is going to be the static mode. And these are for expressions which we can reduce to a value at compile time. And so we want m in that m.map. Actually, we want all of m.map to be type checked in the static mode, and then we'll be able to find it at compile time. So some things can happen statically, like substitution. So this allows us to do some functor applications. We'll see a counterexample in the next slide. But in a functor application, you can just think of that as beta reduction, which is mostly just substitution. We can figure out how to do that statically. On the other hand, we can't do side effects statically. So some operations we're not going to be able to do. There's not really too many twists and turns also in this design. If you look on the ML Workshop program, there's a media attached on this talk, and you can find the typing rules there. There's a sort of a write-up of the abstract that I submitted for this talk, and it has a bunch of preliminary typing rules. Again, we haven't implemented it, still work in progress. But one challenge around this is that sometimes it looks like we're going to want to perform side effects at compile time, and that's bad. So here's an example. So if I have this functor here f, and maybe f defines functions f1 and f2, and then map, the thing I might want to use somewhere else, depends on flipping a coin, right? This would be a bad implementation of map, but it's something that you could type in. Running this functor is actually, in an OCaml program, is a runtime thing that will flip the coin at runtime at the place where you instantiate the functor, and it will choose either f1 or f2. We don't want to do that at compile time for many reasons. And so the way that this would work is we can't have compile time side effects. That's bad. And so instead, the current plan is to take the functor f. If you try to apply f to some argument and then call map in the static mode, then we would sort of look at this, figure out that it's no good, and then reject. We might imagine something more glorious where we do some kind of purity analysis and say that the type of this functor is an impure functor which doesn't work in the static mode. We could imagine all of that. I think much easier would be, let's just try it and see if it wants to do any side effects. Because all of this is at compile time anyway. So instead of coming up with a glorious kind system, we can just sort of try the thing and then fail if it doesn't work. In any case, we definitely want to reject an application of f in the static mode, even if we know f statically and even if we know f's argument statically. We don't know the application of f to x. Okay, so that's the static mode. That's sort of the more intellectual beating heart of all of this. But throwing up a bunch of typing rules, all of which is kind of easy on its own, is not a good use of time. So we're going to move on to the next challenge, which is separate compilation. So the monomorphizations are driven by usage sites, right? And so I might compile map in one file over here, and then use map in some file over there, and then I want to go back and figure out what the monomorphizations are. So how are we actually going to do that? So one approach that we're thinking about is to use the build system. So when I say the build system, if you want to, you can imagine Dune, which is the build system, well, roughly the build system that Jane Street uses. But it turns out that that's not, that's not a requirement. You could do this with other build systems also. But I'll demonstrate the details of this on the next slide. One other possibility, I've said possible here because we're not sure what's best. The other possibility is to use C++ style deduplication. So maybe every time we need a monomorphization of map, we just do it in that particular file where we need the monomorphization. We'll end up with many of the same monomorphizations, and we'll just deduplicate later. It's unclear which will be better. But I kind of am excited about this build system approach. So what do I mean by that? So here I have a usage of map, and now we're going to make a simplifying assumption that this particular m here, that's just m.ml. Right? There was not a functor application. There's no first-class modules here. We're just plucking from m.ml. And in fact, I'm also making a simplifying assumption that map is just defined as a lambda right in that module, that it's not sort of doing some other kind of indirection. So given that, then when I see this usage site somewhere, all we're going to say is that, oh, well, that usage site, to compile that, I need to be able to call this mmap float64 value, right? Where here, float64 is the layout of float hash, and value is the layout of string. Ooh, I realized I should have colored that in blue. I apologize. Or to be clear, I should have colored this in blue. These are types, but this is just the name of a function. Right? And so I've taken the module name and the function name and the layout to sort of build this mangled name. And when I'm compiling, say this is in u.ml, usage site. When I'm compiling u.ml, we'll just record that before linking, I need to have this function somewhere. But as I'm building u.ml, I can just call that function in my .o file, and everything will be fine because I don't only have to execute it after linking. And then the build system just it records this dependency and then knows, oh, to get that function, we just have to do an operation on m.cmo, right? We could work out sort of all the details. I could write like makefile style rules for it or something. It's not all that exciting. What it does do, though, is it does require that the build system be able to deal with these dynamically generated dependencies somewhat late in the process. And so So that might pose to be a challenge, and that challenge might be big enough that it's better to just do the C++ style deduplication. I don't know. So we have these multiple possibilities. So it's worth pausing for a moment before I wrap up, just to consider what happens in other systems. So one other approach to this would be to do sort of more aggressive monomorphization in something like Milton, right? So Milton does whole program compilation. It gets to see everything all at once. That approach is not feasible for Jane Street. We have 40 million lines of OCaml code, and we're not going to slurp all of that in all at the same time. C++ has support for this through its template mechanism, but C++ has no notion of abstraction for its templates, right? The C++ template must be written in a header file. You must always have it as you're compiling. There's no notion of separate compilation or abstraction. And it has to do this lingered deduplication. Rust has full monomorphization, but it still maintains separate compilation and takes a different approach than Milton. But it doesn't require the static mode because we're not going to store polymorphic values inside of structures the same way that OCaml does. And so the problem is somewhat simpler in the Rust context. For C, Java, and Haskell, it's kind of fun to be able to lump those languages together. It's not often that those three end up in the same bucket. But there's not really support for this idea. You just have to repeat the code. I suppose in C and Haskell, you could do some C preprocessor stuff, which goes fairly far, actually, for this. But maybe not the most beautiful solution. So Haskell has support for this kind of thing in its type system, but if you actually want runtime code that works at multiple layouts, you need to just repeat your code. C# takes a very different approach, one that I haven't really touched on before in this talk, which is it does runtime code generation. So that's another possibility, is we could get to the point that we need to do the sort of layout unknown thing, and instead of making a branch at that point, just say, oh, at runtime, we need this specialization, and it just creates it right there at runtime. That requires lots more technology than we're going to develop just for this. This sort of fits into that space. The static mode is probably the biggest part of this that's really something new on top of what we already have. So I'm going to make a sort of a shameless plug here. If you want to work on this, we have just opened up a sort of pre-faculty / postdoc position where you could come to Jane Street for a year or two and work on this and other sort of bleeding edge research questions. So there's more information behind that link there. And that's all I've got. There's the link still. Thanks very much.
So one obvious design possibility didn't.
It's not.
Okay. One obvious possibility that you didn't explicitly mention is that at the declaration site of map, you could just say to the program, please write out all the instances you like. So they don't have to duplicate the code, but they have to write the signatures, and then all of those are available. And that's very simple compared to messing with the build system and Dune and who knows what kind of thing. So it might be a good jumping off point.
Yes, and actually we were planning on doing that as sort of an earlier stage of this. One challenge is that because we can take a type like point that anyone can define anywhere and then use it unboxedly, it's going to be hard for the author of the function to be able to anticipate all the monomorphizations that will be necessary. So you might end up in a scenario where there's got to be some way later on down the pipeline to say, add these monomorphizations, and then you sort of do it explicitly. But it's not just so simple as being able to declare it up top.
So, is that working?
Yeah.
Okay. Is there a assumption? I mean, I'm curious how this interacts with the sort of nested polymorphism, which I understand OCaml has. So in other words, if you're just having regular polymorphic functions, right, you have pre-nix form, and so you can deal with the layouts at the application site. But if you had a polymorphic argument which had layout flexibility in it, the point at which that function gets defined, I mean, the second,
Yeah,
I think you understand.
I do. So I can think of sort of two different answers. So one is like in normal functions, so Leo gave a talk this morning about having polymorphic parameters. We're not going to allow layout polymorphism in that spot. We can just sort of statically rule that, like, syntactically, essentially. We just can't do that. But the other place that it could happen is in a functor parameter. And so in that scenario, it's this static mode check. We won't be able to know what the function is, and so we can reject that at compile time, just saying, there's no way to do sort of layout monomorphization in this context.
Closer? Speak closer to the mic.
Okay, so at some point you probably need to make...
Turn the mic on. Turn the mic on.
Okay, so yeah, let's go. At some point you're going to have to make the two pieces of data that have different layouts interact with... Okay, this one's fast. Interact with each other. How do you trust to and from the layouts you have to do this at point?
So to cast from the casting from what to what? I'm not sure I understand.
You have to have these two pieces of data that use different layouts that have to interact with each other. Say you have unboxed code and lots of code has written in the generic case, how do you generate some sort of accessors that will from one layout to the other?
So just to repeat the question, because the mic wasn't working. So the question is, how do you cast sort of from one layout to another? And it essentially depends on exactly what you want to do. So in the case that you mentioned, going back and forth between, say, box float and unboxed float, there's just going to be a box function and an unboxed function.
How do you get it?
So the sort of the root set of layouts is fixed. So like the compiler sort of says, okay, these are the set of layouts, and then you can make products and sums out of those layouts. But as we do that, we just sort of build in the conversions.
Okay.
Sure.
Okay. Yeah, that's great. I never thought I'd hear the words, I'm excited about the build system being uttered here in this workshop. But my question is, why is deduplication important? You showed map, which is a small function, which conceivably wouldn't be a huge problem if it was duplicated. Do you really have big functions that are layout polymorphic whose duplication would actually be an issue?
That's a great question. I don't really have an answer yet because it's still sort of too early. My guess is yes. Yeah, okay. In my short time at Jane Street, if it is possible, it happens. When you have that much code, we'll build it out.
Cool, thank you.
Oh, okay. Ron can maybe give a concrete example.
Just a super concrete example.
No, not.
Just a super concrete example. You might want to parameterize a bunch of trading logic over the representation of price. And that representation of price might have multiple different layouts. So you could have, 500,000 lines of code that's layout polymorphic, and that might be instantiated at multiple different things, and you might want to have that like multiple versions of that alive in the same program. So like, this totally can happen.
Okay. So what about data representations in data structures? So Milton, for instance, is doing a lot to optimize data layouts in records and so on. So once you have trees, for instance, you might have unboxed floats inside those trees, right? Instead of having.
So I'm not sure I understand the question. I mean, yes, we want to have that.
Well, does this tooling you're doing also lead to efficiencies in types? You didn't mention anything about type specialization.
Oh, yes. I mean, I don't think we would need type specialization even for that. I mean, I wanted to focus more on the sort of the layout polymorphism part than the unboxed type design part, but. We will allow you to sort of, if you're writing a structure, you can use an unboxed version of another record, say, so like that point record that we saw at the beginning. If you just put a hash at the end of that, point hash will just get inlined into some larger structure. So obviously you wouldn't want to do that recursively because then you'd get something infinitely large. But if you want to have a rich structure at compile time but have it all flat at runtime, that works just fine.
Okay, so that's the end of the session. Thanks, the speaker again.